Welcome to the deep dive. We're here to take complex source material, boil it down, and give you that essential understanding fast. Today, we're cracking open the AI programming stack. We're talking code, math, and the very core building block of modern neural networks. AI development needs, well, two key things.
Exactly. It's a dual foundation. If you really want to get AI, build it, use it. You need strong math intuition that's formulating the problem. And you need strong programming skills that's implementing the solution. They absolutely go hand in hand. You can't separate them.
Right. So our mission today is to really dive into that implementation side. We're going to focus on Python as the language. And then we'll peel back the layers on the libraries, the frameworks, the things that make deep learning actually tick straight to the core components.
Yeah, and as we go through this whole stack, I want you, listening in, to think about something. When you consider modern AI, what do you think is the most critical piece? Is it the algorithm, the huge data sets, or maybe the super powerful computers? Because the tools we're about to discuss, well, they're the reason those three things can even come together effectively.
Okay, let's unpack that, starting with the undisputed champ in the AI ring, Python. I mean, most coders know Python's popular, but why does it just dominate AI and machine learning, especially over languages known for speed, like C++A?
Well, it's interesting. It's not really about the raw execution speed. It's more about iteration speed. In AI research, how fast you can go from an idea to running an experiment to seeing the result, that cycle time is everything, the Python being maybe the most efficient prototyping tool out there.
I get the productivity point, but if I'm building something that needs serious performance, my first thought is C++ or Java. So how does Python actually boost productivity when, training ML models seems to be all about raw speed?
Right, that's the common thought, but here's where the insight comes in. Python's speed advantage isn't in running the final code, it's in developing it. First off, the open source community, it's massive. If you hit a tricky numerical issue, chances are someone else already solved it, and that fix is probably already in a library everyone uses. Second, the code itself is just cleaner. You need way fewer lines than in other languages. So researchers can try out really complex ideas in days, maybe instead of weeks. That ease of getting started and developing fast, that's the real productivity win.
Ah, okay. So it's the combination of those extensive support libraries and that huge open source community that allows for the quick, flexible development. And that flexibility sounds pretty crucial too, right?
Oh, absolutely. A language itself is incredibly flexible. It's great as a backend for web applications, for instance. And critically, for data science, it's fantastic at gluing different data structures together, which you always have with messy, real-world AI data sets. It's just the perfect connector.
Right. And if you're doing this kind of scientific coding, this flexible work, you need the right setup, not just a basic text editor. We're talking IDEs,
Yeah.
integrated development environments, but one's really built for data work.
Yeah, the material highlights two main ones. First is Jupyter Notebook. What's cool about Jupyter is how it blends coding, writing notes, and even presenting. You run some code, see the output right there, and then you can write detailed explanations using Markdown. All in one document, great for sharing, great for teaching.
It really is like a digital lab notebook, isn't it?
Exactly that. The other one mentioned is Spider. Now, Spider looks more like a traditional IDE, but it's specifically designed to feel intuitive for scientific computing. And the key thing, it bundles the core libraries we need to talk about next, NumPy, SciPy, Matplotlib, right from the start. It's like a ready-made science workbench.
Okay, so Python handles the quick prototyping, but the language needs its tools, right? The computational toolbox. What's the foundational kit, the scientific Python stack, that does the real heavy numerical lifting?
Right, we're moving from the car's body to the engine now. And the absolute start of that whole stack is NumPy. NumPy is fundamental because it introduces these objects from multidimensional arrays and matrices. This is how you represent data efficiently for computers.
And the real magic of NumPy seems to be its performance boost, especially from something called vectorization. Why is that such a big deal?
Well, think about it. A standard Python loop going through, say, 1 million data points, that's slow. Vectorization lets you perform math operations on these big arrays and matrices almost directly down at the C language level. It bypasses a lot of Python's overhead. Much faster computation.
And making that even cleverer, NumPy uses broadcasting. Can you explain that a bit?
Yeah, broadcasting is subtle but really powerful. It basically means if you try to do an operation on two arrays that aren't exactly the same size, like adding one number to a whole array of 100 numbers, NumPy doesn't just error out. It checks if the dimensions are compatible, meaning they're the same size, or one of them has a size of 1. If they are, it automatically stretches the smaller array to fit the calculation. It's very efficient.
Got it. So NumPy is the high-performance engine. What's the kind of sophisticated gearbox built on top?
That would be SciPy. Think of SciPy as the collection of specialized, high-level math algorithms. If NumPy gives you the basic array structure, SciPy gives you the tools to do complex things with those structures. We're talking functions for linear algebra, solving differential equations, numerical integration, and really important optimization routines through scipy.optimize. It's the advanced algorithm library built right on NumPy.
Okay, engine, check. Specialized gears, check. Now we need the team that actually handles the fuel, loads it, cleans it. That sounds like Pandas. Anyone who's worked with tables knows Pandas data frames. It feels a bit like R's data frames or a superpowered spreadsheet, but right inside Python.
Exactly. And Pandas is essential because AI models, well, they can't handle messy data. Pandas gives you the tools for what we call data wrangling, reshaping tables, merging them, sorting, slicing out just the parts you need, and really crucially, dealing with missing data, usually marked as NaN, not a number. Your whole pipeline stops without good data cleaning, and Pandas provides that.
Yeah, the power really shows up in methods like Group B. You can take a huge table, maybe university data, instantly group it by, say, professor rank, and then calculate stats for each group, like the average grant amount per rank. Boom, instant insight.
It's incredibly powerful for exploration, and when you need to grab specific data, Pandas gives you precision. For someone coding this, knowing the difference between .lock and .ilock for selection is pretty important. Lock uses the actual labels, the names of rows or columns, while ilock uses the numerical position, the integer index.
Okay, that's a neat detail for coders.
Yeah.
But for the listener, the main idea is just that Pandas offers two really precise, fast ways to get exactly the data needed, using either names or positions.
Absolutely, yeah. Precision and speed in accessing data, that's the core concept. And finally, once you think your data is clean and you've found something interesting, you need to see it. Visualization. That brings us to matplotlib. It's the standard Python library for making 2D plots, line graphs, scatter plots, histograms, that kind of thing.
Right, the basic plotting code.
Yeah.
And we often hear about layering Seaborn on top if you want to make those matplotlib plots look, well, prettier for reports or presentations.
It's a common workflow, yes. Seaborn adds that aesthetic polish. Okay, so that covers the foundational science stack. Now, let's move up a level. Beyond the basic tools to the layers where you actually apply them. The spiralized AI frameworks. These are built using that efficient stack we just discussed. This is where model training happens.
The sources mention a few big names, TensorFlow, Microsoft CNTK, but really the conversation today centers on the two main forces, right? Keras and PyTorch. And they seem to have pretty different approaches, different philosophies.
They really do. Keras kind of markets itself as deep learning for humans. Its whole philosophy is about abstraction. It usually runs on top of another framework, often TensorFlow, and its goal is simplicity. You can set up quite complex neural networks with very few lines of code. It's great for getting models up and running quickly, especially if you don't need to tinker with every single internal detail.
So Keras is like the high-level language for deep learning. Makes sense.
Exactly. PyTorch, on the other hand, which has strong backing from Facebook, takes pretty much the opposite tack. It gives you a lower-level environment, and this is really key for researchers or advanced users. It gives you much more freedom. You can write custom network layers. You can really dig into the mechanics of how training works, like understanding backpropagation step by step. If you want fine-grained control and you're experimenting, PyTorch is often the choice.
Okay, before we get to the network itself, there's one more utility player. Scikit-learn. It seems to sit on top of the SciPy stack, too. What's its main job in this pipeline?
Right. Scikit-learn is like the general-purpose toolkit. While Keras and PyTorch are focused on building and training complex deep learning models, Scikit-learn is often used for essential, maybe slightly less glamorous tasks, things like pre-processing the data before it even goes into the network, and then after training, evaluating how well the model performs on unseen test data. It provides all the standard metrics, data splitting tools, helper functions. It's incredibly useful.
All right, this is where it gets really foundational, I think. All these libraries, all these frameworks, they're ultimately designed to build and train networks made of one fundamental concept, the perceptron. Okay, so let's tie this all together. What does this whole integrated stack mean for you, the learner, trying to navigate the AI world? We've walked through the structure, from the base language up to the application. You start with Python for its flexibility, its speed, and prototyping.
Uh-huh. Then you bring in NumPy for the core array computations, that high-performance engine. On top of that, SciPy provides the advanced math algorithms like optimization. Then Pandas is absolutely critical for getting your data clean and structured. And Matplotlib lets you see what's going on, visualize results.
And finally, you wrap that whole scientific stack with the application tools. You use Scikit-learn for utilities like pre-processing and evaluation, and then frameworks like Keras for ease of use or PyTorch for more control to actually build and train the models, those multi-layer perceptrons, using your prepared data. Getting a handle on this whole integrated system really feels like the essential groundwork for moving forward in an AI career.
It really is the operational blueprints.
Right, and specifically, the next logical step seems to be a deep dive into linear algebra. We're talking vectors, matrices, linear transformations.
Exactly. And here's the thought we want to leave you with, something to chew on. We know matrices were incredibly efficient for representing complex, high-dimensional data. Now, consider a fundamental concept like linear regression. How might applying relatively simple linear transformations represented and calculated using matrices allow us to model and understand complex, real-world relationships far more powerfully and efficiently than just trying to use repeated, basic arithmetic alone? That's the kind of power hidden in the mathematical foundation. Something to think about.